Let's go and talk more about the linear regression. We already done a lot of work, hopefully a lot of understanding what we are after. So basically we are after finding some sort of a correlation between our independent data points, our dependent data points that we measured in some experiments. Where we are also heading to is to understand that there are some experiments which are better conducted, some experiments that are worse conducted. There are some variables that are better to be chosen into some models. Some variables are not a good idea to choose for a particular model. So this is where we should head. But before that, we have lastly spoken about transforming. We already did some kind of half step. We already talked about transforming our linear regression task from having all these ugly sums in some matrices and doing some what have we done, like some specific differentiation with respect to one parameter of our regression, second parameter of our regression. The good news and what will help us is that we know matrices and vectors, and this will very ease our work. Yep. So we started to express our data points in the vector form. So what we can, for example, imagine we have one independent variable and we have conducted capital N of experiments. Yeah, we have capital N of the data points. And now, if there will be more of these independent variables, there was some example, temperature, concentration, maybe some nonlinear transformations of these variables. Well, we can keep this vector form, so we have still the vector of the experimental data from 1 to n, but we can now stack them together, and we basically form a matrix. In more general form, we would be stacking. So now this x1 would represent like the first variable which has n measurements. This looks a bit messy in the beginning, but once we are comfortable with the fact that okay, our data are in some matrix, then we can just work with this matrix here. This matrix, we will call it capital X, and yeah, okay, we have it here. I didn't have to write it there. We will call it capital X, and we can even express, for example, our prediction equation. So if we have this matrix X, remember all the variables and all the experiments in the corresponding rows, variables in the columns, then this X, so-called regression matrix, we can quite nicely multiply with our parameter vector P, and we obtain a vector of our prediction. So each of the n experimental data points that we measured, the y without hat, there will be a prediction of this y hat. Is this clear, understood, digested? Everybody comfortable with that or no? No? Yes? I will take it as yes. At least Adriana was nodding. Thank you. Good. So if we now have this this form of our prediction equation, we can build our matrix vector form of the least squares, of the least squares that we have done for the linear regression when we had just the one line with two parameters. Now there can be any number of parameters. And lastly, we also seen that writing this vector transpose the same vector would mean the sum of squares of the components of that vector. Yeah, for example here x transpose x would correspond to the sum of the squares of the components of the vector x. So let's hope this is well digested. So let's wipe these guys. We should get into this formula very quickly and very easily. So let's first well, what we have some multiplications of the scalar multiplication of the vectors, right? It should be scalar because we are just the sum of square is just the scalar value. We are just minimizing the sum of squares. So let's first find out how we can write this multiplication down. How we can do the multiplication. How to do that? Well, if we have the transpose of the first bracket, we can transfer this transpose on the corresponding vectors, right? So if I write something like this, that represents the first bracket. That's okay, hopefully. And the second bracket stays the same. Now, please help me with some multiplication. What will be the product of the two brackets? Yes, there will be a lot of scalar multiplications because, well, our...
we can do it just for example, like one element now.
Not one element. Let's keep the vectors. Well, let's really do this. What if we had if these? So we have vectors now. If these were scalars, then we would know. Yeah. This would transform into our famous formula, but yeah, there is only slight complication that we cannot really write the vector square, but still we should obtain some equivalent of this scalar form in the vector world. How would that look like?
Multiplied by y.
Mm-hmm.
That's equal to y squared.
It's not equal to y squared, but this is the first term. Yeah.
Minus yt
right? It's just and now
Minus y2 with hat multiplied with y. And the last one is plus. Those with the hats multiplied together.
y hat transpose y hat. Exactly. Yeah, and we really obtained some equivalent of this formula. So our first term a, let's say it was y, so whenever we would write a square, well, we have y transpose times y. The same goes for the last term, the y hats term, and we also have some cross terms. But they are too different. These are two same, and the question is whether they are same but different, but still the same. So, are they same or are they different terms? What do you think? Who would say they are the same? Hands up. Who would say they are the different? Okay, and we have four people abstaining. Well, it's a democracy. You have the right to do so. Okay, let's try out. So if we have so y transpose times y hat, what would it mean? Our y's are always the column vectors, so of course the y transpose will be a row vector. So we are getting to, this will be y1, y2 until yn multiplied by y hat 1, y hat 2, y hat n. Okay. To move more stuff. Oops, let's see how it goes. Move, okay. Missing the square. Where is the square? So what do we get? y1 times y1 hat plus y2 hat plus and so on and so forth. Yeah, typical cross product. So it of course contains the cross product of the elements of the y and y hat. And our second term, y hat transpose times y. So, no, same. Our vector y hat and y1, y2 until yn. What do we get? Y hat 1 times y1, y hat 2 times y2, and until y hat n, yn. So they are same but different, but still the same, which means we can group these two guys together. And it's completely up to us how to do that. And let's say the first term looks nicer. We will see. We can transform it back and forth whenever we want. Good. We should be also, of course, the bracket. So we have y transpose y minus 2 times y transpose y hat and plus y hat transpose y hat. Okay. So far so good.
Can we go a little bit up?
More? Okay.
Isn't y with head transpose and y with the head squared?
Why?
The y.
It's we don't have a concept of squaring a vector. Yeah. So this is a concept of squaring a vector. Because, well, what would you like to calculate that? Usually when we are squaring the numbers, we are getting the distance from the origin, but this is still not quite the distance to the origin. Well, it's distance squared. Yeah, well, no. It's a bit. Let's just say we don't have this concept well defined, like putting the 2 as the upper index of the y. For good reasons, it will help us, because we would make use of this form. So let's then introduce. We are still missing our variable p, yeah, so we cannot really do the differentiation yet. Let's introduce, well, our prediction equation. So our y hat is our regressor matrix times p. Let's introduce it wherever we need. Good. Let me keep this one here. That's our scalar analog, and let's move this one a bit. We will need it in a second. Good. Our y transpose y, they are staying. This term stays and will be relatively irrelevant for our determination of the parameters. Doesn't contain parameters. What we have here? Minus 2 times y hat times y transpose times y hat, which we now say is x times p. And our last term, well, that will be a bit complicated. What would y hat transpose be equal to in the terms of x and p? Oh, sorry, let's do it this way. Fill the missing places. P transpose X transpose. Very good. P transpose X transpose. P transpose X transpose. That was for the y hat transpose, yeah, for the first guy here. The second guy is just y hat, so we just plug in x times p. Yes or no? Adam's face saying her.
The p is vector as well?
Mm-hmm.
Okay.
Yes, yes.
I totally like the lower index of this.
Good one. Thanks. Better? Thank you. Yeah, tell me whenever I write it in a strange way. Good, so we have just used these guys. And Well, maybe it doesn't seem so, but we are now ready to do the differentiation with respect to the vector p. For that, we would need couple of rules. The differentiation with respect to vectors, it's again same, different, still the same, a bit different than the differentiation with the scalar variables. So the simple rules are, if we have what we will need, we need some in the, what do we have in the scalar case? We have a constant times x. If it's differentiated with respect to scalar x, then we get the constant back. Yeah. In the vector case, this will be the representation, like the vector of constants is multiplying our x. This will be the case for this guy here. Our variable for the differentiation will be p, and well, this cannot be anything else. This y transpose times x must be a vector, otherwise we would not get the scalar objective function, the sum of squares, or part of the sum of squares. So if we do this differentiation in the world of vectors, we actually get the vector a itself. Yeah, so here it's transpose. This is the sum, or the elements of vector x are weighted by the elements of A. So we are trying to find contribution for each of the elements of x, and the contributions are for x1 it's a1, for x2 it's a2. Yeah, so that's why that's the interpretation. Those will be the slopes of this function in the different dimensions of x. This is the, let's say, easier and intuitive one. The second formula from this calculus with the vectors and matrices we would need is to take the derivative of this quadratic form. It's really called a quadratic form if we have x transpose times a times x. Yeah, because that's what we really have there. The x transpose times x will be another matrix, a very important matrix that we will talk today about. And in what is this a scalar equivalent of? It's a scalar equivalent of constant times x squared. Yeah. What do we expect? What is the derivative of x squared with respect to x in the scalar world?
2 times constant times x.
Yes. And this will depend a bit, because the result looks like this, which there is this notion of 2 times a, but yeah, it depends on the matrix. What would be the property? So there will be a special type of matrix where we can just write 2 times a.
Well, I have a question. Could we just use the derivation rule for the multiplication?
Yes, and we will, well, you will get the same thing.
Yeah.
Yes. Yeah, you would actually transform into this form, and you will get, this is it, because first you will get, from this you will get a transpose, and from this part you will get a. Yeah. Exactly. Yeah. If we are at the mathematics lectures, then we would derive it. We can. There is a very nice book called Matrix Cookbook. All these kind of formulas are there. What would be maybe a special special case. There is a special case when we can really have this even more similar scalar analog. So what is the property of matrix A where I can write it this way?
The size is 1 by 1.
Even more general. Yeah, why? Because if A would be symmetric, so A symmetric, then A is equal to A transpose, right? If we flip the, what is it, rows and columns, well, we will get the same thing because it's a mirror image of itself. And of course, well, since I'm mentioning it, it might be that probably this matrix, the X transpose X, is symmetric. How can we find out? So, is the X transpose X symmetric? Give me the proof. Now we can do the mathematical proof. Very easy one. And it's not proof by contradiction or anything. It's just the direct proof. How can we deduce that? And the separation processes sucked all the energy from you. There should be the energy balance of the students done before and after the separation process is examined. Well, so let's just ask, if this was a symmetric matrix, then if we do its transpose, then we should get the equality. So is this an equality? That's the question. So what if we apply our good old formula A times B, sorry, A times B transpose is equal to B transpose A transpose. What do we get? How is this applied? We take the second matrix, we transpose it. Second matrix, transpose it. Oops. And we take then the first matrix and we transpose it again. What do we get? X transpose transpose is again the X itself. Our mathematical proof was just done. Quod erat demonstradum. So, lucky case. You look quite sad looking at these matrices, but we should be very happy because this makes our life much easier. So we can just apply this simpler result when doing the differentiation. So let's do the differentiation. I will just copy this guy here, if I am able to do so. Why am I not able? Because I didn't press copy, right? That would be necessary. Copy. What am I doing wrong? Copy and paste. Can I do it like this? Finally we understand each other. Good. So let's do the differentiation of this term with respect to the vector p. I do the first part, you do the rest. There is no p here, the derivative of the y transpose y is 0. The second part, which of the formulas here we can apply? Minus 2 times y transpose x times p. P is our variable here.
Minus 2 remains.
Mm-hmm.
And then yt turns into y, and x turns into xt.
Yes. So let's do the differentiation with respect to p. We want it, of course, to be 0. So 2 remains. No need to write anything. And then what should I write?
Y?
No.
Oh, sorry. Yeah, y.
No. So let's put it this way. Yeah, this guy is the A transposed. So when we are writing the result, we should write the A itself.
So x transpose y.
Perfect. X transpose y. Second term looks harder, but is actually simpler. What do we apply? How do we apply? What's the result? Of course, we can do some bracketing to just realize the same form. Yeah. So just we know that our matrix is symmetric, so we can write a times x. Yeah. Or in our world, our A is x transpose x. Do we need the bracket? No, we don't need the bracket. X transpose x times p. Does it make sense to everybody? Okay, good. Thanks. Thank you for the confirmation. Well, doesn't look that bad. Yeah, just x, y, x, p, very relatively simple. We can write even more complicated stuff out of this, and it will simplify further. Just believe me. Well, what we are actually having here, if we are now just a bit creative.
Can we just put in front of bracket the x transpose?
We can, but it won't help us. Why? Because we want to separate this guy. It's a good suggestion, and it will show us something important. We can.
I'm just thinking because on the left side of the equation we got 0.
Mm-hmm.
So
Yeah, but the division by vectors, or well, you will end up with what? Division by, so X is not square matrix, so that's a bit That's a bit not easy to do, but we can do it even simpler. What did actually our differentiation formulas tell us? This result here cannot be anything else. Well, it's a vector. It cannot be anything else than a vector. We did a differentiation with respect to the vector p, so we here need to have a vector because it will tell us contribution of each of the elements of the vector p. Yeah, that's the vector which generally we can call A. What do we have here? Again, our differentiation formula is telling us it's A times x, matrix times our variable in question. So if we just rewrite this, so x transpose x p, and let's put the negative hero on the other side, x transpose y, well, we just recover our good old A times x is equal to b set of linear algebraic equations, which probably you are not surprised too much. You probably have seen it in your optimization class. Yeah, I have some quadratic function in multidimensional space. I do the differentiation. Basically, Newton's formula is doing this. So how do we solve A times x is equal to b? Backslash in MATLAB, that's correct. Okay, so the MATLAB way, p is equal to, and now what we are backslashing. Mm-hmm.
And b is to the right.
Mm-hmm.
So inverted A matrix is now
Inverted? Why? We are backslashing, so we don't need inverse. So what we are doing, mathematics or okay, x transpose or MATLAB, yeah. If we do MATLAB, this is one way. If we write it in a proper mathematics, well, we just x transpose x inverse x times y, which is quite an interesting formula. The parameters, the optimal parameters, the best parameters, the parameters that we calculate are kind of just the linear combination of our measurements, with some, of course, what we can expect here. There must be some arithmetic averages. This can be our result, but this MATLAB can even simplify further. This sort of operation has a special name. Remember or recall that our matrix X, well, our matrix X, the regression matrix, is not squared, yeah, because it has as many rows as we have the number of experiments, observations, and as many columns as the number of parameters. So it's not square in general, and basically that's why we need to do this trick to make the x transpose times x will be squared. Now we can apply the square root and so on. And the special name for this is actually of this operation, of this whole underlined red thing, is a pseudo-inverse of X of the matrix X in math is usually denoted with this kind of dagger, like if you want to stab somebody, like a little sword. And the MATLAB way of doing this, it's just saying P is equal to X/Y. Yeah, we don't need to bother with this one. And this is why we have gone through this tedious derivations, because now what do we need to do if we have MATLAB, Python, or whatever programming language at our hand? Well, we just collect our independent variables in one matrix capital X. We gather our observations in a vector Y. We call this command 1, 2, 3 hits of the keyboard, enter, and we have our parameters.
So we cannot break just this.
You mean okay? These two brackets, and the X transpose disappear. Yeah. Yeah. Something like that.
Doesn't it affect the math or it or
No. So the slash command looks so simple. Yeah, like just a simple line. What is behind that is actually whole decision tree, which is so. What does this do? It will analyze what the structure of this matrix is. So first, it will find out this matrix is not squared, so I'm doing pseudo inverse, and then it will find out I don't think it's doing exactly this, like, because this takes a lot of operations, yeah, multiplying, maybe to multiply a matrix by itself, transposes can be somehow simplified, but definitely it's not doing. Well, definitely it's doing inverse in the most efficient way that it can do. And there are different algorithms based on how the X is shaped, this matrix decompositions stuff. Yeah. So it's yeah, pretty efficient way, and also your MATLAB is usually telling you whenever you are using whenever you write either inv, like inverse of a matrix, or you write hat -1, where you want to invert the matrix, it will usually underline and say, well, better use the backslash because it will be more efficient, more numerically stable. This is the reason. The backslash is the most efficient way, because it will really see what is the matrix behind. Okay, it's not that we are giving you in the exercises really challenging matrices, but yeah, maybe in your either semestral projects or later you will find out that it's good to know about this backslash and to use it. Okay, so ready for some more matrix stuff, but I don't think it will. I hope it won't hurt more. We don't do the differentiation with the matrices and vectors. Let's just maybe first analyze this matrix here. It's very special. It holds a lot of information, and we should know about it. This matrix is actually called a covariance matrix. and let's maybe dive into it again, or let's recall what is the shape of the matrix capital X. How does it look like? I can just copy what we have. Where is it? What we have written down before. We started with this in the beginning of the lecture. Well, it really holds. Each column is corresponds to different variable or to some maybe transformation of that variable, and each row corresponds to one specific data point. It's kind of table like Excel table, which is telling you what were your experiments about. So we can write it like this. So our first column will hold one variable in its n different experiments and different representations. There will be a second variable, whatever it is, and our, let's say, last variable, should I better call it like MP, such that I distinguish between the subscript p and the vector p. X and p and sorry, not n. This is first experiment, second experiment, the last experiment. So let's try and practice some matrix multiplications. Hope you are brave enough for that. So how will the X transpose look like? What we will, like, qualitatively. We have columns for the different variables in the matrix X and rows for different experiments. If we do the transposition, well, they should just exchange, right? So our first column will just hold, well, that will be the first row, so it will hold information about each variable in the first experiment. This guy stays, but we have second variable, first experiment, we have last variable in the first experiment. The second row will, well, what will just happen with the indices in our former matrix X when we moved from one column to another? What happened? Our first index just increased by 1. Yeah, this is the transposed. Yeah. Yeah. It's not the result of the multiplication. Yeah, yet we will come there.
The next X is 1, 2.
Yes, 1, 2. So what does it mean for the second column? in the former matrix X, when we shifted from the first column to the second column, our first sub-index changed from 1 to 2, then from 2 to 3 to 3 to 4, and so on, yeah, until we ended up with MP being the first index, telling us what? Wait, is it correct, or did I already write the? No, first variable. Okay, yeah, good. First variable and variable. So now what we should observe is that we will be shifting the second index in this transposed matrix. So of course our diagonal, or if we can talk about the diagonal, is staying untouched. Our NP2. Yep. So it's the inverse world. These are all the data points from the first experiment, all the variables. Second experiment, third experiment, and so on, until we arrive at the last experiment. Okay, and let's now do the multiplication with this guy. Diagonal will be what?
Squared.
What squared?
Like piece 1, 1, piece 2, 2. Each element of the matrix is going to be squared.
No. No. Let's. Okay. Well, how do we multiply the matrices?
Okay.
It was a good guess. I almost bought it for a second.
It's not the equivalent of MATLAB, like multiplication with that, yeah?
It is equivalent of MATLAB. Well, MATLAB is doing multiplication of matrices as.
Multiplication in front of.
No, we don't do element-wise. Element-wise, it's no. That's not the real multiplication. It's called Hadamard product or something like that. No. That's crazy math actually. If you want to do the derivation with it. So how do we multiply the matrices?
First row.
What's the algorithm? Yes, we take the first row and we multiply it with the first column. So what will we get from the multiplication? Ah, so there are the squares. So we get x11 squared plus x12 squared, right? We are multiplying first row and the first column. So you were just slightly off with your guess. So what will it be if we now turn back to our old ugly notation with the sums? We can write it definitely as a sort of a sum. What do these x's have in common? Which index? First or second? First one, and it's the index 1, and the second index would just iterate. We already know that we get squares, and this will go from k1 until capital N. Good, sum of squares. What will happen? What will happen next? Which one do we want to do we want to do? Oh, let's see. Let's probably do the first cross product. So let's find out about this element. What will it look like?
Which one?
This one here. Still the first column, but the second row. So we take the second row from the first matrix, and we take still the first column from the second matrix. So this one's, oops. So this one still remains. What do we get? x21 times x11, x22 times x12, and x21n, x1n. What do these terms have in common, and what is? So do we get sum of squares? No. Yeah. We get something like the cross products between now what? Well, this first row is this second row is telling about the second variable that we have in our data set. The first column here is just saying again about the first variable. But what they have in common, they are just coming together at the point of, so how is it? x2 1 times x1 1, x2 2, x1 2. Yeah, so they are still they are still joined, or they share the same observation point. So that means that we probably can. The red dot just means that that's the red multiplication. It's not very well seen on the beamer, but in the notes from the lecture it will be seen. So that says that we can again kind of bind them with this kind of sum, yeah. And then we just say what would be the formula? What should we write? x2k
times xk2.
This guy, that will be the second there. There is very little. There is no xk2. x1k. Exactly. Okay. Which one next? Let's try to do this one here. So the first row, second column. First row, still the red guy, and the second column. This is the blue dot.
It's gonna be same, but other indexes are gonna be switched.
What is switched?
Indexes, like it's gonna be K2.
K2. No.
And
K2. No. This is not. This cannot be. This cannot become K2. Whatever K is. So, first row has what? There is always the first index is 1. Yeah. So we should be getting suspicious. Like, okay, there should be x1, and what is this second column? The first index is always 2. So let's just assume that we will get something similar, and then write it, and then we can check it. I just clean it up a bit. Okay, one and so would it work? Just scroll down a bit so I can show you better. First row, second column. x1 1, x1 1. If we start with k equal 1 times x2 1, x2 1, x1 2, x1 2 times x2 2. Works, and so on and so on. So actually we get the same term here. Should it surprise us or not? Should it surprise us or not? Very suggestive question. Right? It shouldn't be much surprising, because, well, we already know, we have proven it. Yeah, very strong thing. We know that this matrix is symmetric, so whatever happens above the diagonal should have its mirror image under the diagonal. So with this logic, we can of course continue. What should be the element? I know it looks messy. We will tidy it up. So we have first row, first column, first row, second column, second row, first column. What should come here? Second row, second column. I revealed too much. x2k squared, perfect, and so on and so forth. Well, we already even know, if we now plug in, let me scroll to where we started to talk about this vector notation. Yeah, this was our first attempt to take vector x times vector x and doing the scalar multiplication of a vector itself. We just get the square of x. So if we now say, this could work, even if we now take our vector x as the first variable. Well, so basically we can be writing our covariance matrix in the form x1 transpose, where x1 is just the vector which represents the first variable measured in n experiments. And the same way we can start to fill the diagonal. x1 transpose x1 times x2 transpose x2 until x number of parameters, number of variables. Yeah, this is going to be, this is how our diagonal going to look like, and we can start applying very similar thing here. Again, we have seen this, we have done it just in a different context. Well, sum of yk xk, it's this sum, so some cross term, but they are sharing the same time index, experiment index. We can conveniently again write it with the through the scalar products. So all these guys are now become x1t x2 x1t x2. No need to again take care about the specific order. Scalar multiplication can do this. Until what? This is the row which belongs to x1, x1, x1 times with x1, it's so by itself, by x2, and by the last variable. What else we can fill in? Let's fill in. Well, this should be, the first column should be just mirror image of the first row. It's symmetric matrix. We cannot find any more surprises. Which means, did I put this a bit too much down? X1 transpose X and B. What's gonna come here? It's like a Sudoku now, yeah. The sum has to be, or there should be all the numbers used. Yeah, X to transpose X and B. Yeah, we should have also the mirror image, of course here. Yeah, that's how the symmetric matrices look like. So it's quite fun. What are the consequences of this matrix? If you see it for a first time, well, you take one matrix, you make a copy of it, transpose it, multiply them together, and you might think, well, all the information about the X which I had there is lost. But it's actually not true. You actually gained a lot of insight into your data, because what if we now do what is the notation that we use here? I don't want to mess up the notation. Let me check the notes. V, okay. So what if we now do just slight variation of this matrix? Very simple compared to all the heavy stuff that we have done today. Let's just divide it. If we have a lot of experiments, we can divide it by the number of n. If we don't have a lot of experiments, the question is, what is a lot of experiments? Then we divide it by the n minus 1, so the number of experiments divided by 1. Well, this is easy operation. This is just scalar. So this scalar will just basically appear in all these terms. But what would be then? What would the term x1 transpose x1 divided by n minus 1, which is nothing else than 1 over n minus 1 sum of x1, x1 square, k goes from 1 to n. Have we seen such a thing ever before? Any standard deviation? Exactly. Or, well, it would be standard deviation if it's square rooted. This one is nothing else than the variance of x1. No. So and that's just the first element of this matrix. The first element of this matrix is telling us how the x1 is behaving. Yeah. Let me just recall, where was our standard deviation? Maybe this guy here. our standard deviation. Yeah. We call this Bessel correction. The only trick here is that the formula that we just got now is simpler because we already can assume, well, let's center our data. Let's remove the mean from our data. Oh, and then we get this one. That's fine. Let's maybe add the note that x is the data x are centered. So basically, in analyzing this matrix, we can, if we continue along the diagonal, what do we recover? We would basically just recover the standard deviation squared or variances of the different variables, yeah, x and p. That's fine. We can also do that individually. Very interesting will be the off-diagonal elements. So the off-diagonal elements are now coming from these cross terms. So they should tell us something about the relation of x1 with respect to x2. And these will be, what's the good notation? Yes. And this will be, again, let's have some sigma notation for them, but let's also attribute these cross terms to the variable, to the corresponding variables. So the cross term here will be between variable 1, variable 2, variable 1, variable 3, variable 1, variable 4, until the number of variables. Now it becomes too many indices. And of course this is symmetric, so whatever happens here will also happen on the upper side of the diagonal. And well, it wouldn't be that if x1 squared is a variance of x1, then these cross terms, these sigma x1, x2, for example, that will be so called a covariance. X of x1 covariance of x1 with respect to x2. So if you center your data, even if you let's say you do not normalize, just center your data, you can already find this sort of a matrix. It will give you a bunch of numbers, and maybe these numbers, if the data is not normalized, won't be quite comparable. So what we can do is to see even a clearer image. Is to say we either normalize our data before, or what we can just do, it's maybe easier way, we can do like the normalization of this covariance matrix. And the normalization of the covariance matrix will be matrix let's call it maybe C. There are different notations, and this will be called correlation matrix. And the correlation matrix, without any heavy matrix calculus, let's construct it just like this. If we have the element of this matrix on a row I with the column J, well, we just take the corresponding element, which would mean from our covariance matrix Vij, and so how is this working? Vij, so Vii or V11 is the covariance of x1. The second element, or the second row, first column, the covariance of x1, x2 is at the V12. 1, 2, 1, 2, because it's this guy here. 1, 2 or 2, 1, yeah, because it's symmetric. So if we now take standard deviation of not x1 but xi, standard deviation of xj, we basically get the normalization, and we can guarantee that these numbers will happen between -1 and 1. Of course, if we take diagonals, so let's just take example of C11. C11 will be, we take sigma square x1, the variance of x1, and we divide by standard deviation of x1, standard deviation of x1. What do we get? Yeah, so for the covariance matrix, we can pretty easily expect that our diagonals are the diagonal of this matrix is full of ones. It's the same thing as if we would normalize our data. So normalize means that all the data points have the unit standard deviation or unit covariance. The interesting stuff is going to happen under and above this matrix. I just put this sign raw because these Cij, these off-diagonal elements, will turn into something that has a special name, and it's a so-called correlation coefficient. Correlation coefficient, as we already discussed, will take numbers between -1 and 1. That's good. Why is it good? Because if I see this matrix and it's not particularly large, let's say I have maybe 10 variables, then this is 10 by 10 matrix, then I can start to compare the variables between itself. You have done it if you already had these exercises. You've already seen it in some example of a distillation column. What I can start to conclude? Well, if the correlation coefficient, yeah, and this will be again like correlation coefficient Ij Yeah, those are these elements of this matrix, this Cij. So if it's greater than 0, we would say, of course, it's a positive correlation. What does it mean, positive correlation, in the simple terms? What does it mean if the two variables have positive correlation? What can you tell? Maybe in the more child language or simple language, let's say. Like temperature and pressure. Yeah, there are many systems where they have positive correlations. So if the temperature increases, pressure increases.
Something like the way it's pointed, for example, it's positive, then we increase the temperature, we increase the pressure as well.
Yeah, exactly.
If it's negative correlation, it's the other way around.
It's the other way around. Yeah, if one variable increases, another decreases. Yeah, there are, of course, physical systems or systems where somebody will tell you what these data are. You can deduce it. You can judge it. Yeah? If you do the distillation column example, you will find out, oh, the pressure at the top of the column and the pressure of the bottom of the column are positively correlated. Well, that's another discovery of age. We kind of have this intuition because we have studied separation processes and stuff. But if you are given data that you have no clue where they are coming from or what is hidden, it's much harder. So because these correlation coefficients have this nice property that they are just between -1 and 1, so if we just look at their absolute value, and we would find out, well, okay, this is, let's say, greater or equal 0.8. These are just rough numbers. Well, then you could conclude we have a strong correlation. If these are, let's say, between 0.5 and this 0.8, maybe you can suspect that there is some correlation. Maybe you would say it's a mild correlation, and below 0.5 I wouldn't be depends on the quality of your data, but I wouldn't be putting much more attention, like much more correlation is happening. Depends. If Rastio at the exercises gives you some nicer data, maybe at the 0.5 something can happen, but usually this doesn't mean complete equivalence, like there is no correlation, but you cannot really say that the two variables would be correlated. Wanted to do a small exercise with our, where did we find this? Sorry, we were just discussing this age. Sometimes at these reports from our faculty, you find interesting numbers. So this is about the mobilities, where the students, where is the picture? And this is strange PDF, where the students, no, this is this, where the students either come to our faculty from abroad, or we have the what is this? Students from our faculty going abroad. Yes, this is okay. So students from our faculty going abroad in different study years or academic years. So we have one data set, and I don't know why our deans and wise deans somehow put this into one graph with the number of foreign abroad students coming to our faculty. Yeah, so here we have some numbers. I've done this. I wanted to have a bit more time that we calculate the correlation coefficient. It's just 5 numbers. It's not the big statistics, but if you look at this, so this is represented graphically. You might start to notice, like, well, maybe it seems like if this variable is decreasing, also this variable is decreasing, and if this one is decreasing, it might be that we have increase, maybe we have a light decrease. This is just the note. I did this calculation for these two variables. You get the correlation coefficient 0.7. So it is suggesting there is some correlation, but then the question would be, does it make sense that these variables are correlated? Is this just correlation, or is this causality? So is there some magical power if there is less students in one academic year deciding to go abroad for Erasmus and so on? Is there some magical power that will, if there is less students from our faculty going abroad, that will hold the students from all the world coming to our faculty? And it doesn't seem that it's there. We can, of course, deduce that there is some kind of common factor which will influence these. Yeah, that was the COVID pandemics that reduced these numbers. So just the nice words at the end. Be careful with the correlations. Not all of them mean causality. Some of them mean something else. Completely else is happening. Yeah, it doesn't have to. The correlation does not have to indicate that one variable has really influence on another. Any questions? Okay, if it's not the case,